Okay, section 4.5, number 10. And 4.5, number 10 is write the equation of the line that represents linear approximation of the following functions at given point A. Graph the function and the linear approximation x equals A, or near x equals A. Use linear approximation to give the to estimate the given function value, and then compute your error is what it wants you to do also. So on this particular one, we're going to start off. We'll go ahead and rewrite this. What we're really saying is we're saying f of a equals a over a plus 1. And in our case here, if a is 1, then we get 1 over 1 plus 1 is 1 over 2. All right? F prime of a. So, you know, kind of going back to what we've done here before. I've got something on the top, I've got something on the bottom. If I want to move that up to from the bottom up to the top, it'd be like, you know, x to the minus 1. So I could rewrite this just as a over a plus 1 squared. And so if I plug in a 1 to this now, I'm going to get 1/4. All right. So now for linear approximations, this is all we need. We really need this. We need the a, we need the f of x, the f prime of x, and then we need the x minus a. So if you remember what a linear approximation is for y, we say it's equal to the L of x. And we gave you this funky equation here, which is f of a plus f prime of a times x minus a. And that really comes back to that point slope form. Okay, that's where that one came from, which in this case is going to be equal to 1/2 plus 1/4 times x minus 1. Because we calculated the derivative up here, we substituted in the f of a and the f of a and the f prime of a, and then x minus a. So this is our linear approximation. So now if I want to calculate the linear approximation, and actually I could probably, I wonder if I can, let's simplify it all here. Doesn't look like it here. So what I can do now is go ahead and calculate what that is for f of 1.1. Well, what we could say is, so this would really be kind of step, I guess we've kind of done step A, which was up here. Step A on 10 was write an equation of the line that represents a linear function. So this is that equation. I guess step B is actually to do some graphing, and you could do this in Desmos. What you would find, let's do this real quick. Keep my annotations here. See if I can go into Desmos really quick. So if the first function I will graph is my initial function here, which is a, which is x divided by x plus 1. And then the next one, because we're only looking at it at near 1.1, so we're really only looking at this part of the graph here. Then the next one I would graph would be my 1/2, 1 divided by 2, oops, plus 1/4. All right, so back into here, I just took some time and did the graphs in Desmos. So for part B, you need to graph this. And the neat thing about this is the graph is actually kind of cool, because what we're doing is we're looking at the function, and that wants us to use linear approximation to figure out what it is at 1.1. And you can see, because we're working with a equals 1, as long as we're close to 1, we're going to be relatively close to what the value is. because that line is going to stay relatively close. So you can see if I'm here, I'm okay. If I'm here, I'm okay. But as I get further away, no longer am I at a good approximation. Like at -1/2, my approximation is way up here, but really it's way down there in real life. But if I'm close to 1, this linear approximation is going to be outstanding. So that's that graph that you need to get. And again, the best way to do that is just to go into Desmos and figure out how to graph that thing. And it looks something like this. I won't be able to draw it near as pretty as we saw it just there. It does something like this, and then your linear approximation does something like that. And they kind of touch in one location. All right, part C then. Part C says, use this data, part C, use the linear approximation to estimate the given function value. So we want to work with f of 1.1, which is right up here. So what we're going to do is we're going to do f of 1.1, which we say is approximately equal to L of 1.1. And then guess what we do? Then we substitute that guy in to my L of x equation. My L of x equation is right here. So 1/2 plus this times 1.1 minus 1. So 1/4 times 0.1. Do all the math there. What you get is you get a number like 0.525 if you plug 1.1 into this linear approximation up here. And then the last step, step D, is to calculate the percent error in your approximation. So what they do is they give you kind of a nice little formula to do that, where they say, well, take your approximation minus your exact, so 0.525 minus your exact, and your exact would be, well, it would be if you actually plugged the 1.1 into the original equation. If I do that real quick here, well, I guess it's 1.1 over 1.1 plus 1, that's 1.1 over 2.1, okay? And this is absolute value, again, 1.1 over 2.1. Absolute value. And that divides by the exact value again, which is 1.1 over 2.1. So if I compute the, and that's also an absolute value. Oops. If I compute the top and bottom there and come up with the actual number there, and I think you got to multiply that by 100 here too to get it into a percentage. Let me go into my calculator real quick. Keep these annotations. I get 0.525 minus 1.1 divided by 2.1. So the top is a 0.119. I'll divide that now by 1.1 divided by 2.1. And I get 0.0227 that I then would have to multiply that whole thing by 100 to put it as a percentage. 0.00227 becomes approximately 0.23%. That's your percent error that you were off. So what this is really saying is the linear approximation is this line here. Okay, this is your L of x. This is your f of x. The exact value, you have to use f of x. Okay, but if we're close to a equals 1, if we're close to a equals 1, we can get a good approximation using a line and using a linear graph to get that approximation. So good, as a matter of fact, that we're within 0.2% of the actual number.